So today folks, hello, welcome again to my YouTube channel. Today we are going to talk about the mechanical energy of a simple harmonic oscillator. First things first, on our last video we captured simple harmonic motion derivation using calculus for a mass spring system. So today we are going to derive the formula for mechanical energy for the same. Now for a mass spring system, let's say a horizontal mass spring system that looks like that, with a mass attached to its end. Normally energy can neither be created nor destroyed, but it's transformed from one form to another. Therefore, we normally say that mechanical energy in any system, the mechanical energy in any system is given by the summation of the different forms of energy in that system. In this case, for a mass spring system, the mechanical energy is given by potential energy is plus kinetic energy. Kinetic energy is simply energy possessed by a body in motion. Potential energy is the energy possessed by a body due to its relative position. So in this case it is denoted by the symbol U. So from what we know, kinetic energy is given by a half mass times velocity squared. So when we talk about a harmonic oscillator, we normally look at the velocity in terms of oscillatory motion. Therefore, when we look at a system that is moving in simple harmonic motion, its displacement is directly proportional to its amplitude times its motion through a certain angular velocity at a certain time, certain displacement, which is given by A is equal to x is equal to omega A cos omega t plus phi. Now, in order to get our velocity is given by the first derivative of displacement, which is v is equal to dx over dt, which is equal to d into bracket. Now this a cos omega t plus phi, which in this case will be given by, when you differentiate the time function, which is our omega, will come outside. Then when you differentiate cos, you get negative sign. Therefore our derivative will be, for velocity, will be equal to negative omega a sine omega t plus phi. Now replacing this in our equation for kinetic energy, what do we get? We get that kinetic energy is equal to a half the mass times this now function of velocity omega a sine omega t plus phi. Now this is squared. Now after squaring, what do you get? You get that the kinetic energy is equal to a half m. When you square the function which is in the bracket, you get omega squared a squared sine omega t plus phi, but the sign is squared. Now that will be your function. So from a simple harmonic oscillator, we normally know that omega squared is given by the spring constant divided by the mass attached to the spring. Therefore, replacing omega squared with spring constant divided by mass, we get that a half mem multiplied by k all over the mass a squared sine omega t, this one is squared, plus phi, gives us our kinetic energy in that form. After putting the expression there, you get K kinetic energy is given by a half K a squared sine omega t plus phi. Now this now gives us the kinetic energy for that mass spring system at any given time t. But if we are at the mean position, the time is equal to 0. At time t is equal to 0, the sine function becomes 0. Therefore, at the mean position, we have maximum kinetic energy. Now, from this expression, we can say that the maximum kinetic energy, max, will now be given by half times kinetic energy a squared. Now this will be equal to our mechanical energy, since all the energy in the system will be converted to kinetic energy. Therefore, at maximum kinetic energy, a half Ka squared is equal to the mechanical energy of that system. Now coming back to potential energy. So potential energy is the energy gained by a body due to its relative, possessed by a body due to its relative position. Now coming to a mass spring system, according to Hooke's law, we know that force times extension x, say the distance moved by that body, gives us the work done by the spring. But what we do know is that for a graph of force F against extension A, the force is directly proportional to the extension. Therefore, get a line with a positive gradient, and normally say that the area under the graph is the work done. Now let us express this as x and our force F here. Now the area under the graph is given by force, which is the area under the graph is half F, which is the force, times E, which is the extension. So a half F times E gives us the extension of a half Fx in that case. But what we do know is that force over spring is given by the spring constant K multiplied by the extension of the spring X. Substituting this here, get that a half Kx multiplied by x, multiply the 3, get a half Kx squared. And this now becomes our potential energy UE. and potential energy is maximum at the region where the extension is equal to the amplitude. Therefore, at the region where A is equal to X, that is where we have maximum potential energy. Therefore, if this is the case, we say that the energy of the system will be, the mechanical energy of the system be equal to a half K, which is the spring constant, times X, and our X in this case at maximum potential energy, the displacement is equal to the amplitude of the system, therefore A squared, and this gives us total mechanical energy. Now we combine all the three equations, whereby you see that the total mechanical energy will now be equal to the kinetic energy plus the potential energy. The total mechanical energy from the systems, as we saw, was a half K A squared, and here kinetic energy is a half mv squared, and mechanical energy is a half kx squared. Now let's say we want to get the velocity at a certain point in time of a certain particle in the system. Therefore, we make velocity the subject of the formula, so you can divide all through by a half, get that m, get ka squared is equal to mv squared plus kx squared. Now ka is equal to mv squared plus kx. Make v the subject of the formula. Take this to the other side, you get mv squared is equivalent to ka squared minus kx squared. Divide by m both sides, get that the velocity squared is equal to, factor out spring constant, get amplitude squared minus displacement squared. Now this divide by the mass. Now from this point onwards, get the square root. Velocity is equal to the square root of k all over m amplitude squared minus displacement squared. But we do know that omega squared is equal to root k over m. So replacing this here, you get that velocity is equal to omega squared multiplied by the square root of a squared minus x squared. And that is our general equation to find the velocity of a particle at a certain point in time of any kind of particle. Thank you. Watch, subscribe, and share for more.